How is everybody today? I feel like the class is like backloaded today. Like most people are sitting above the median line. Maybe it's the awesome power of embedded systems. It's like blowing you back in the lecture theater as time goes on. That must be it, right? Yeah. Sounds good. So, I might as well get started then. We were discussing yesterday the design of single-purpose processors, right? The design of these processors kind of generally following the structure of general-purpose processors, but of course specific to one particular algorithm. So, we left it off with this this example, the greatest common denominator example. Just to quickly refresh our memories, we had derived from the GCD algorithm a flow chart or a flow state diagram, a finite state machine with data path diagram. You can see, hopefully, that this is a relatively direct interpretation of the original C code, right? It's basically a one-to-one mapping, and it's actually fairly easy to automate this translation process if you know how. From this, we decided what our key registers and operations were through examination of the operations and registers used in the program itself for register read variable, right? Through that process, we found that we have various control signals which control the selections made by multiplexers and when registers are loaded with data. These data lines are, in this diagram, going off because we are separating our control logic from our data path logic, right? So it is possible to integrate the control logic and the data path logic all into one big jumbled mess, but it is useful a lot of the time to keep them separated for organizational purposes. These things can become big sprawling messes if you allow them to. So, in this particular example, we have X and Y selectors, we have X and Y loads, and we have the results of the not equals comparison and the results of the less than comparison coming back into the control mechanism, right? So, any questions so far? So far, so review of last lecture, hopefully. So, in order to take this state diagram and derive from it a state diagram that would be useful in the controller itself, we have to extract those parts of the finite state diagram which perform data path operations, and we have to translate those into the corresponding signals that would need to be sent to our new custom data path module, right? So, in other words, we have to know when, inside of this controller state diagram, we need to load Y with something, when we need, what we need to select using the multiplexer, and at what time. Everything is tied to state, right? Very important idea. Another thing that we need to keep in mind with respect to the state diagram, you notice these numbers in binary crawling down the side? We now have separately indicated state values, whereas before we used like numbers with some labeling to indicate jumps. We now translate that into binary code. This binary code can, of course, be represented using either individual flip-flops or registers. Back here, our controller is composed not only of the next state and control logic itself, that is, the combinational components, it also contains a certain number of sequential components. In this case, and in this example, the sequential components that we need to keep track of are the bits that compose the current state number, right? Does that make sense? Doesn't make sense to store that in the data path. It's not used by the data path, it's used by the controller. So things should be grouped with the things they're used by. Good. So, having applied these transformations, it is now possible from our newly revised finite state machine diagram for the controller, we can now derive from that a state table, right? Well, I'm not sure that this slide tells us anything that we didn't already know. Oh, except, of course, we may note that the signals from the data path are actually hooked up to the controller, which is something that we could have assumed. So I still think that this slide is useless. Unless anybody can figure out a way that it's not useless. Perhaps it's the indication, like the labeling here is going to be important on the next diagram. So for our combinational logic in our controller, the outputs from the state register indicating the state value will be using the letter Q. Inputs to the state register will be using letter I. So from the combinational logic's perspective, these Q signals are inputs, these I signals are outputs. So we can therefore derive a great big table. And I apologize if the print gets so tiny. I imagine those of you in the back of the class are probably going to have a fair amount of difficulty viewing this. So if you could bring it up on your own personal computer, that would probably be expedient. People on the internet will perhaps be able to do the same, because I'm not sure how well this is going to render in video. But anyway, so this state table represents the combinational logic that we need to derive for the controller itself, right? Our first and primary inputs to this process are the 4 bits which represent the current state value, right? So we notice, of course, that we're like basically just doing binary counting through all of this, right? So let's consider the X load output itself, right? Well, we notice that we are only loading in state 3 and in state 7, or 8. It's 8, pardon me. So if we take a look, those correspond to the state panels in which those operations occur, right? With register load operations, it's correct to assume 1 when you're loading and 0 at all other times, right? This isn't a situation where you have a don't care value, right? You do care that you're not, like if you were to put a don't care value in wherever y load is not being set to 1, then a don't care value basically says you could be loading, you could not be loading, I don't care, right? In this case, we definitely care. We want to make sure that we're not loading anything into the register at times other than those specified by the diagram. So 1 when loading, 0 otherwise. The same is not true of the selection of the selector multiplexes, these multiplexers. the selector signals to those don't actually matter in cases where the register isn't being loaded, right? So at times other than during register loading, we actually don't care what the selector signal is. Make sense? Good? Yeah? Any questions so far? Is this is, can I get a thumbs up? Awesome. So you know, that's good so far as it goes. We also have the inputs coming in, right? Which, you know, obviously. The next state bits are also of some interest here. Let's take, for example, one of those states where we're actually making a jump, right? So let's consider this one, right? We go to state 0, 1, 1, 1 if x, L, T, y, x is less than y is 1. And we go to 1, 0, 0, 0 in the other case, right? So taking a look at our state diagram, we've got x, L, T, y right here, right? We've got 0 and 1. Notice that this state is indicated twice in the state diagram, right? It is counting, but some of the states are repeated, especially when decisions are being made, right? So in the case where you have this arrangement, right, you go to state 1, 0, 0, 0. In the other case, you go to 0, 1, 1, 1. So that's how things like if statements are being encoded here, which is, you know, basically also how things work in assembly language, right? Assembly doesn't natively have an if statement operation. What it does have is it has conditional jump statements, right? You jump to one spot in the program conditional on a particular, you know, condition, and you jump to another spot in the program if that doesn't work out, but you need two different jumps for that. So that's how you do conditionals, and loops are done similarly. Does that make sense? Good. So from that, all that we have to do is to design combinational logic such that this, all of these states yield the outputs according to the inputs, right? Now that we've formulated things in terms of binary input and binary output, from there all we have to do is hook together some logic gates. So that being said, the design which we have just witnessed the creation of is not an optimized design, right? There are many different things inside of that design, you know, things that could be nipped or tucked. Yet, you know, on we move. We'll have a discussion at the end of this topic about the types of optimizations that you can make on such designs. But just as a preview, this is a lot of states, and not all of them are necessary, right? So we'll see how it goes. So, good. So let's consider a different problem entirely. This one will do more like on the board. Problem statement. We wish to make a bridge, a single-purpose processor that converts two 4-bit inputs arriving one at a time over the data in signal line. There we go. Along with the ready in pulse into one 8-bit output, data out along with a ready out pulse. It's actually quite common in these types of components to have a separate signal that indicates whether or not the results from the module should be accepted as valid results. That's that's like very useful in basic IC design. So, essentially, just to visualize it, right? You have, let's say you have the data line, right? The first thing that happens is it sends, some sequence of 4 bits, right? This is actually a 4-bit line, right? Into the module, right? Ready in goes high for that. Then it goes low, and we don't care what's on this, right? Then another 4 bits come in over there. Ready in goes high again. Then it goes low again, and we don't care what this is. This module needs to have kept track of both of those. The first one in is the low half, and the second one in is the high half. So the first half would be written in like so. The second half would be written in like so. And then once both have been collected, the data out line will push the value of this register at the same time as the ready out line goes high again. Make sense? Basic operation, right? Not too difficult. So as you can see, in this finite state machine diagram, we have 8 states, right? So how many bits do we need? 3, yes, because you count 0. So it's 0, 1, 2, 3, 4, 5, 6, 7. There we go. So our controller is a lot less complicated right there. So our initial state is a waiting state. While the ready in is 0, we remain in the waiting state. When it becomes 1, we go over to the, we enter the next state, assign data in to data low, which is a register, then automatically enter the next state where we're waiting for the ready signal to go low again, right? As long as it remains 1, we do not accept any more inputs. Once this goes low, we then wait for it to go high again. Once it goes high, we record the value of the input line to data underscore high, which is another register, automatically enter a second waiting period for the ready signal to go low again. Once it does, we will have received both bits that we need. We perform this calculation, which I have problems with the way that this has been written, because if you were to interpret this in terms of C, you would think that this was bitwise AND operation, right? But that's not what they're talking about in the problem description. This should be properly termed something like a bitwise OR operation with 4-bit left shifting on the high bit, or right shifting. No, it's left shifting, right? They're basically just like, I guess AND just kind of stands for bit concatenation for some reason here. And I don't actually think that it would be useful to do like bitwise OR as combined with a left shift operation, because that's too much, right? Like, frankly, I don't even think you need a register here. You can probably just like serialize or parallelize the 2 registers output lines, and like there you go, I'm not sure that the second or that the 3rd register is even necessary, but again, this is not an optimized design, and we shouldn't criticize it too heavily. Make sense? Anybody got any questions at this point? Good. You aren't all playing Minecraft, right? Okay, just a little bit? Okay, all right. I guess a little bit of Minecraft is okay. As long as you're doing redstone logic and redoing what we're doing on the board, I will allow Minecraft. Anyway, so the actual guts of the the data path here is very, very simple, right? We don't actually have any arithmetic operations. We don't actually have hardly any logical operations. All we're doing is smacking two registers together, right? So data path, very simple. Controller, hopefully also reasonably simple. So if we break this into the controller and data path, you'll see we have the high bit, the low bit, or I guess word, we'll call them word, the high word, the low word, and then the double word coming out, right? With a word size of 4. That means that we have 3 control signals, one for each one of these registers, right? These control signals are, of course, being controlled by the controller, right? The data that's coming in does not need to touch the controller. There's no reason for it to enter the controller module. And there's no reason for the ready-in signal to touch the data path module. In this case, both the data and the control signals are more separated than they were in the last example. So we have our data coming out of our data out register, and we have the ready out signal coming out of the controller. So he's about to get his notebook out. Uh-oh. So let's consider how we would derive a state table for this example, right? So one of your esteemed colleagues already transmitted the information that only 3 bits are necessary for the state register in this design, right? So we'll follow the convention of the previous. Call it Q2, Q1, and Q0. Right? Any other inputs to the control module? Dun, 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 dun. Yeah. Ready in. Cool. So sometimes I like to do a double line between the inputs and the outputs. It makes it look a little bit prettier, though it's not strictly or technically necessary. So, outputs then. What do we got? Ready out, obviously, right? Ready out. What else do we have? Nobody? Not one person? Data out. That's output of the data path module, not of the controller.
You have the states as well, the next states? Or I guess not.
Yeah, that will be one as well, yeah. But on this diagram, outputs from the controller module include, right, the control signals for the registers. I hope you're all paying attention, because this is probably going to be on the exam. Not this example specifically, but there will be a question like this on the exam. So we've got 3 registers, data high, data low, and data out. Each one will have a corresponding load operation. So we've got low load, we've got high load, and we've got out load. Anything else that's considered output by the control module? the new values of the state register, perhaps? So we've got, I'm just going to do them all in one thing without the lines, because, you know, yeah, fine. I'll do it consistently. It's just easier that way. So it should be obvious now why the particular naming convention is used with respect to 2, 1, and 0, right? It's the bit positions inside of the registers. So, assuming that these things have been labeled numerically, starting with the first one, right? Our first state, 0, 0, 0, right? Our input, then, we have to account for both, right? So I'm gonna do it kind of like that. We'll see how much board space I need. So in the case where all of these guys are 0 and this is 0, right? The state doesn't change. We're waiting for the ready in signal to come in. So there we go. And when we're not writing to registers, we have them as 0, 0, 0, 0. Obviously, the bit that we want to send out, or the byte that we want to send out isn't ready yet, so that's also going to be 0. Right? Next state. Oh, wait, no, I'm sorry. I did it wrong. Here. I should split it. That way I don't make mistakes like this. So. 0, 0, 0, 0, 0, 0, 0, 0. There we go. So, what if we receive the ready in signal? Do we load anything into the registers at that point? Yes or no? Everybody say yes. Everybody say no. We load the data into the first register in the second state. Right? So, in fact, all we do by this point is we go to the next state, 0, 0, 1. And all of these guys are still zeros. Next state. If we've got the ready in, so if ready in goes 0 while you're in that state, what happens? Nothing, right? It has no effect. Basically, in this case, in this state, it doesn't matter whether this is 0 or 1, right? So in fact, let's just rewrite that. I know I'm making a mess, but I'm doing science. So we actually don't care, right? In this state, what is the condition by which we enter the next state? Yes?
That low is equal to 1. Oh, wait, yeah.
No, that's an output. It can't be a condition because it's not an input.
Oh, I see. So there isn't a condition. It's just when you start recording, right?
Yeah, it just automatically goes to the next state. So we automatically go to the next state, right? Because there's no exit condition from that state. Make sense? I think this might be a useful example. So, are we loading any registers? Yeah?
Yes.
Yes, which one?
The data low ID.
Very good. There we go. And obviously the bit isn't ready yet. Right? Next state. 0, 1, 0. Does it matter what ready in is in this one? Why, yes, as a matter of fact, it does. So, if ready in is 0, we'll do one thing. If ready in is 1, we'll do something else. Right? If ready in is 0, what happens?
Just goes to the next state.
It goes to the next state, which is 0, 1, 1. Are we writing to any registers in that case? Nope. Zoop, 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 a zoop, a zoop. What happens if ready in is 1?
State stays the same.
State stays the same, absolutely. Point, point, point. There we go. Good. Next state. So, we're now in this state, right? Do we have different behavior based on the state of ready in? Yes. So we'll split this. What if it's 0? What do we do?
Nothing.
Nothing. You stay in the same state. 0, 1, 1. Nothing. Is anything happening with the registers or the ready out signal? No. Not even a little bit. In either case. How about if it's 1? What's the next state? It's the next state. Yeah. There we go. 100. So, we're now in this state. What's our exit condition? There is no exit condition. When we are in state 100, we proceed immediately to 101. The state of the ready in input signal does not matter 1 iota. Are we doing anything with registers? What are we doing?
1 to high, data high.
Very good. High, 1. There we go. Boom, boom, boom. Excellent. So, next state. 101. How do we get to the, so, does this rely on ready in? Yes. So we split right there. 1, or I've been doing it 0, 1, so I should keep it consistent there. 0, 1. If ready in is 0, what do we do? It's not actually explicitly labeled, but you can assume that it's the same as the behavior for this one. What do we do? In the case of 0, next state. 110. Are we loading anything into registers? Are we outputting anything? Like, is ready out set in this case? Big 0. Nope, 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 nope. And if it's 1, we stay in the same state, which of course is 101. 0, 0, 0, 0. Next state. Is this one affected by the state of ready in? No. We don't care. What's the next state going to be? Are there any conditions? Nope. 111. Are we loading or any registers? Yes. Which is it? Data out. There we go. Data out. Boom. Are we doing anything with ready out?
Yes.
What are we doing?
1.
We're giving it a 1. Finally. And Finally, our final state, 1, 1, 1. Does ready in matter? No. Everything goes 0, and we reset the state. State table derived. Any questions? I mean, that's logic, so. Question?
So what would you use that table for? Is it just a different way to, show that information rather than that diagram? Or are you gonna make a Carnot map out of it?
You would make a Carnot map out of it, derive minimized state equations, and from those minimized state equations you can derive combinational logic circuits. In fact, why don't we try that? Ha-ho! So, let's pick, for example, let's do one of the easy ones. Let's do one of the registers. Actually, you shouldn't even need a Carnot map to determine what the condition is for this guy in terms of inputs. Right? What's the condition for a high load in terms of the inputs? What's the equation? You follow it across, right? Q2, Q2, Q1 naught, Q0 naught, and that's high load. Right? That, of course, you can, we demonstrated doing the circuit from that. I don't want to draw a bunch of AND and OR gates, but I can if you really want me to. Let's just do the state, diagrams. So, or whatever you call these. So, out load, right? Out load is actually, in this case, equal to ready out, which is equal to Q2, this was big, I was way too enthusiastic with these numbers, or these letters, it's too big. I'm going to be more reserved from now on. They're like, that's not why we come to this class. So, right, you just take, because the ready-in signal doesn't matter, all you have to do is derive the signal purely from some kind of combinational logic on the state elements themselves, or the state register, the register that shows you which of the bubbles you're on. So, in addition, if we wanted to do low load, we can read across. It's not Q2, not Q1, Q0, right? So you can imagine the circuits in your head, I hope. This one's a little more tricky, obviously. With this one, I would, break it into an actual Carnot map, do the, that thing. We would, do I2. We would have, Q2, Q1 on one side, and then, Q0 and ready. I'm just going to call it R, B, ready on one side, and you'd right? You'd fill in one of these guys, you'd do the groupings, you'd derive the minimized equation from that, and then that's something you could make a circuit with. Make sense? Yeah. So, yeah, the correct way to think about this process is having been built up from the Carnot map approach, right? Basically, what we've done is we have put a bunch of layers in front of the Carnot map so that by the time we reach that point, we are dealing with things like the actual state of an actual controller. Does that make sense? Question?
So would this state kind of be like a program counter?
Yeah, it's
like how before we were talking about the register for program counter. Is that sort of what these states would be?
Yeah, essentially. So if you think about these bubbles as being instructions in assembly, they're not, right? They do more than assembly instructions, and they do different things than assembly instructions. But if you think about them in the same way as assembly instructions, then yes, essentially, this would be your program counter, right? It keeps track of your position inside of the finite state machine. Make sense? Awesome. Any other questions? Yes?
We can talk about this after class, but I have no idea what you did for the table at all. Like, I don't understand like, how many of the values. I was following the entire time. I just lost.
How many other people are completely lost? A few people. Okay, I'll explain it quickly then. We'll see. I'll try. So, all right. The thing that we are trying to do is derive combinational logic for this box, right? We take, like we're modeling it in this manner, right? We have the next state and control logic, that's a combinational circuit, in the same way that the functional units are in the data path are its own combinational circuit. No state holding elements, right? In addition to that, we have the state register, which keeps track of which bubble in the finite state machine we're currently on, right? So, that's what this is. This keeps track of which bubble we are on in the finite state machine, right? This is the ready-in signal, which is coming into the control logic, right? So, where are we here? No, come on. Where are we? There we go. Okay. So the ready-in signal is a signal into the IC itself. So if we like this rectangle right here, that's like the boundary of the entire controller that we're building, right? That's the same box as this box, right? So we've got the ready-in signal, we've got the data-in signal, right? So our design decision is to feed the ready-in signal directly into the control logic block rather than into the data path block. Are you with me so far?
I think.
Okay. The ready-out signal is also derived purely from the controller logic because it doesn't actually require any data, right? So if we consider the controller itself, right? We have the quote-unquote pure input of the ready-in signal. We have the pure output of the ready-out signal. We have the stuff that's going to the data path, which are the register load signals, right? That's the stuff that's going down. Those are like the intra-IC communication, right? One combinational circuit communicating with the other. In addition to that, we have the state register, which tells us which of the bubbles of the finite state machine we're currently on. And we have the inputs into the state register, which tell us what the next state is going to be on the next clock signal, or on the next rising clock edge, right? Because everything gets loaded according to the clock. So, essentially, interpret this as current state column, interpret this as next state column, interpret these binary numbers as decimal numbers if it helps you count, right? And basically all this is telling us in state, 0, 1, 1, 0, 0, the high load signal needs to go high, otherwise it's 0. That's the information that we're deriving. It can be derived directly from the finite state machine diagram. Like nothing we have done on the board over there is not on this diagram, except where they've left information out, like here, where they didn't put ready equals 0, but we kind of assumed that it would be there anyway, right? Does that make sense?
I'm just okay. So the high load and the low, like the low load, the data load. When did they like? I'm just a bit confused when they like change values like from 1 to 0. From 0 to 1.
When they're being written here, here, and there, in terms of the finite state machine diagram.
All right.
That make sense?
I guess. I'll just ask some questions after class. It's okay.
Well, it's practically after class now. So, for the benefit of anybody who's, like, these are actually very useful questions, and I would prefer they were asked with me with the mic on, so that anybody who's interested can hear it, and maybe if we could keep the camera rolling for an extra 5 minutes, if that'd be okay. So, anybody who wants to understand this any better, please hang around for the next 5 minutes. The rest of you, who are definitely going to get 100% on the exam, please feel free to go have dinner or whatever. Whatever it is you do when you're not in class. All right. Take her easy, folks. That was only a vague threat about the exam, by the way. Yeah. So that you can design the logic in a way that was even more minimized, right? Like, consider it, okay, so the question that I just received is, why would you want an output in a don't care state? And this is kind of going back to the multiplexer example, right? So, consider a Karnaugh map, right? Let's just do like a small, simple little one, right? Let's say, well, now let's do a slightly larger one. Let's say you had 1, 1, 1x, 0, 0, 0, 0. Because this is a don't care state, you can do a Karnaugh group that includes it. Which means that you can simplify the logic quite a lot, because that's a lot simpler than the two groups, right? So, like, with don't care states, you can arrange them in such a way that it, like, minimizes the number of state logic gates that you need, right? Does that make sense? Yeah, awesome. Any other questions? Questions?
Yes, I'm just following.
Okay. All right. Any part in particular?
I'm just like completely lost. It's like if I could get more specific, I would. But
okay. From the top then. So we have our stated aim for this module, right? It's the process that I described here, right? It actually doesn't really matter what the functionality is because we're talking about the process, right? That, pardon me, that process has been done out for us in terms of a finite state machine, right? This will be something that an engineer put together, right? This is like, this is what, yeah, okay. I was second guessing myself because this wasn't on the next diagram, but it is on this one, so I see that that was just an error in the diagram. I thought I was going crazy there for a second, but no. So the finite state machine is something that would be designed, right? This is equivalent, like, we demonstrated the equivalency of these with C programs, right?
yes. Yeah, I kind of get it.
So, okay. So you can take a C program or a program in any like sufficiently basic pseudocode, right? You can convert it into finite state machine diagram, right? Using statements, loops, and conditionals, right? So, essentially, what this finite state machine here, what this actually is is it's a very simple C program that's written something like, while not ready in, right, and then nothing, so it just loops until it is, right? Then you go to, data load is equal to data in, right, next statement. Then you wait for it to go back down to 0, so while ready in, right? Is that with me so far?
Yeah, I think so.
So we have a correspondence. Somebody designed this algorithm, right? This is an expression of that algorithm, right?
Okay.
Our object is to design hardware that implements this program without needing something that we can program with C. Right?
Yeah.
So, that's kind of the whole point of the single-purpose processor. Right? So our first step with that, since we want to break this down in terms of state-holding elements and combinational logic, is we need to separate this out, identify those components that are combinational, those components that are sequential. Right? That's step number one. So, in this particular case, the elements, that's where this break starts happening, right? So, the data path itself in this case is very simple. We don't really have to go through the design of it because it's so damn easy, right? All we have is registers with no operations, right? In the previous example, we had things like addition and subtraction and comparison. Those would be operators in this bad boy if we required them for this example, right? We don't, because it's just assignment. Like this algorithm, if we did out the whole thing, would only contain assignment operations. So this thing only contains register load operations.
Okay, so what's data load, data high? We have the outload and I think we have the outload, the low load, and the high load. I don't really understand what any of them are or what they mean exactly.
That would definitely impede with your that would not help your ability to understand this example for sure. These are registers.
Yeah.
Right. So they're flip-flops. It's a sequence of four, in this case, 4 flip-flops that have an enable signal, right, that loads whatever information is coming across this line at the point in time that the load signal is high.
Okay.
Does that make sense?
I think so.
Yeah. So, I'm trying to think of some kind of example. Think about a cash register.
Okay.
All right? A cash register has a series of drawers, right? Let's imagine each drawer can have either a dollar in it or not a dollar in it. And the arrangement of dollars in the cash register constitutes some kind of storage of memory, right? It's going to break down an analogy quickly, but the load signal is the button on the cash register that opens it so that you can put things in it, right? And let's imagine that this is a very fancy cash register which has magnetic sensors in it that can detect what the state of the cash drawers are and can output that at any time. Because that's also true of registers. You don't need a signal into a register to tell it when it outputs. It just always outputs its current state, right? It's always on in that sense. But the load operation, you have to press the button, right? So the control logic is just when do we push these buttons to load the values.
Okay.
Does that make sense?
Yeah, I think so. So I'm just with the values in the table.
Yeah.
I'm just a bit lost in how we get from here to there more or less.
Okay. I'd like to see what this gentleman's question is before we proceed to that. Yes?
So when you set all of the lows to 1 or to high, how do they get set back to 0?
Also by combinational logic. So if I have, for example, load low, right? That will be high only if not Q2 and not Q1 and Q0, right? So in terms of actual logic circuit, you would have Q2, Q1, and Q0 all coming into an AND gate, big one. The output would be low load, right? And we have not Q2, not Q1, and regular Q0. Make sense?
Yeah, well, mainly what I was wondering is because in the finite state machine, we set them to 1, but it never gets set back to 0. So I'm wondering why in our chart we don't like have it 1, and then for the rest of the states it's also at 1.
It's kind of just like assumed knowledge about registers. With registers, you only load them, like that one, if that one was 1 for longer, like if we had don't care about values instead, it would constantly be loading from data in. So for example, just in terms of like a sequence of operations that would be possible if that were the case, right? Let's say that the low load stayed 1 until like here, right? Somewhere in this vicinity, the data has changed, right? The data in line has changed. A new ready in signal has been received. So that means the data has changed. Which means that if this were still 1, you would load that data into both registers, right? Which completely defeats the purpose of what you're trying to accomplish with the IC, right? Because you want to load one, load the other, smack them together, output that, right? If you did it that way, it would be load one, load the other and the first one at the same time, smack them together, and basically you would get like, you know, for an input like 1100 and as the first bit and 0110 as the second bit, if that were the case, you would get 01100110 as your output bit instead of the correct answer, which would have been 11000110, which is what you actually wanted. Or this flipped. Yeah, it would be the other way around. But you get what I'm saying, right?
Yeah, that's helpful. Thank you.
Yeah. Okay. Thank you for your question. Back to you.
Yeah. So I'm just a bit lost how we get from like the finite state machine we have to like the actual like values that we put into the table.
Good. So this comes from direct observation of the things going on in the specific states themselves.
Okay.
So essentially, it's easy as long as you know how to read the diagram, right? So it always makes sense to start at the beginning, right?
Yeah.
This is the first state.
Yeah.
We don't have any statements inside of this state that would indicate that we're loading a register, right?
All right.
Because there's nothing in it. This is just a label,
Yeah.
right? So it's doing nothing except controlling flow to the next state. That's the purpose of this state.
All right.
Right? So essentially, it's this while loop, right? It's waiting until you hit the next one, right? Or waiting until the signal flips and then you hit the next one. So in this case, this one, right? In the state table, we just write down the state we're currently in.
Yeah.
Right? Ready in can be either 1 or 0,
Okay.
right? Because it's an input. We want to account for both cases,
Yeah.
right? And in this case, it actually has a pretty extreme effect on the state itself,
Yeah.
right? Because
when it's 0, it loops back in.
exactly.
Okay.
That like the whole execution of the algorithm is dependent on what the state of ready in is, right? So we have to account for it. If it's 0, in this case, we loop back into the current state, right?
Yeah.
So even assume, like, not worrying about the fact that like all of the registers we're not doing anything with them.
Yeah.
In that case, the next state is the same as the current state.
Yeah. Okay.
Make sense?
I'm with you over here. Yeah.
Okay. If ready in is 1,
Yeah.
then we go to the next state here,
Uh-huh.
right? That state's, you can think of them in like codes. That state's code is 001,
Yeah.
right? So that becomes the new value that's written to the state register.
And it says data low load, so like why don't we have it low load in the table for that one?
Because that's the purpose, like, okay. You don't put it there, you don't put it, we don't write both of these, like, in theory you could,
Okay.
right? But we've separated them out for the purpose of this diagram. This diagram contains too many states.
All right.
It's part of the optimization that we're going to talk about with these types of diagrams is anytime you have a state that flows directly into the next state with no condition on the transition,
Yeah.
that's a redundant state,
Okay.
right? And like from an electronics perspective, yes, you absolutely could have, as soon as you set the states to this state, you could put that high as well, right?
Okay. Yeah.
Yeah. So I'm not claiming that this is a fully optimized design.
So it's more or less in that one doesn't matter, so we can just put it as 0 in the table, or.
Which one doesn't matter?
Okay, so it's like, so if we start at 0, 0, 0, if we go to ready in is 1, then it goes to the next one, which is data load equals 1.
Yeah.
Okay, so it goes in for the output of 0, 0, 1 and not the output of 0, 0, 0.
Sorry, repeat that.
Alright, so it's like the first box is 0, 0, 0.
Yeah.
So if ready in goes to 1.
Uh-huh.
So is this one? So this is when we're changing the value to 0, 0, 1, right?
Yeah, the value of the state register. Yeah.
So by the time it gets into box 2,
Yeah.
is it already at 0, 0, 1, or is it becoming 0, 0, 1?
It is already in the state 0, 0, 1.
Okay, so that's why it doesn't care for 0, 0, 1, and it just goes to like, and the value goes low for, or the low
Yep.
goes to 1, and then it goes to 0, 0, 1, 0.
Yeah. So I think that the problem is that you're being too smart.
Thank you.
You're trying to optimize the design at the same time as understand it, right? In this case, like what I've done on the board over there, just a literal translation of what the finite state machine is doing.
Yeah, which I think I'm not 100% understanding what it's doing then.
Yeah. So
when does the state change? Like in this, is it like each box the state is changing, or?
yeah.
Okay.
This is a state. That's a state. That's a state. These are all separate and distinct states.
Okay.
Yeah.
Oh, so that's the reason why we have don't care values for some of the ready ends.
Yeah, because some of these states don't require any input from ready in to get to the next state.
Okay.
Right.
I think I was thinking it was like it got to rec first for end, and that's when it changed to the next state, and then it was only changing like 3 states, and somehow it restarted or something.
Ah, you're confusing the register rights with the states. So the registers in the data path are also state holding elements, right? They hold, but they're holding data, right? Data that we want to output at some point. Yeah, while we are only performing like 3 assignment operations here,
Yeah.
we are passing through a number of different program states because a lot of them are just waiting for the ready signal to go high or go low again,
Okay.
right? So those waiting states, while they are not actively pushing values to signals in the data path module, they're still perfectly valid states. Not all of the states here are like some of these states are redundant, right? We don't need all of them, but what we've done over there on the chart is a faithful recreation of this algorithm as designed.
Okay.
Does that make sense?
Yeah, I think I understand it more once I understood that each box was its own state.
Yes, that's definitely that will definitely help when you're trying to understand finite state machines.
Yeah,
for sure.
So even though some of the states have data they have a load of 0, right? So is it still getting loaded into the registers, or is it only get loaded to the registers at the specific states that have the load go to 1 or something?
Yeah, it only gets these registers only load the data that's coming in externally when their control signal goes high.
Okay.
Yeah.
So that's more for the state of the controller than the state of the data path register, or?
This is entirely the state in the controller.
Okay.
Yeah.
So it only changes the state of the data path every once in a while then?
Yes.
Okay.
Yeah. Yeah, I was the whole purpose of this demonstration was to show controller design, not data path design.
Okay.
The last example was data path design.
All right.
Make sense?
Yeah.
Yeah.
Okay.
Good. Any other questions?
So for data high, data low, and data out, what's the what's the difference between the three, more or less?
Data low is holding the first word that comes in.
Yeah.
Data high is holding the second word that comes in. And then once both have been received, they both get loaded in some manner consecutively into data out, which then holds its value so that that value can be propagated over the network stably. The reason that I didn't catch this while I was doing the lecture itself, but the reason that you separate that, right? You don't want the outputs to be derived directly from these registers only, because these change, these outputs change during a load operation, right? So the way that this is currently configured, this data out value remains stable until this state,
Okay.
right?
Yeah.
So all through this guy hasn't changed or modified. So anybody who's relying on him can rely on him, not changing, right? That being said, the whole purpose of the ready out signal is to indicate when that value is ready. But, it's also good to maintain stable values just from a good design perspective.
So basically the controller is just saying when for it to load values from a data line, from an external data line, more or less?
That is exactly and precisely.
So then we're loading the 4 significant bits and the 4 more significant bits, and then in the seventh state, which would be 6, we're loading it all into 1, and the last state we send it out, more or less. We send it out at some point. I don't know when.
So the way that registers work is that they're always being sent out implicitly. So when we load it,
yeah.
that means in the next clock cycle, anybody can read it.
Okay, and then it's not changed again until the next, until it goes through all the states again.
Yeah.
Okay. So then what does ready out do? Does ready out just say it's it loaded it or something?
Imagine a scenario like this. This is a bridge that bridges 4-bit inputs, right, into an 8-bit output. What if you had a bridge that bridged 2 8-bit inputs to a 16-bit output? This same module, but with the bit widths expanded by a factor of 2. And imagine this module was an input to that module.
Yeah.
The ready signal, ready out here, would become the ready in signal of the ×2 version of this. Right? You kind of have it like this. You'd have 4-bit, a 4-bit signal into the bridge it then becomes an 8-bit signal, right? It's got a ready signal.
This is more like we're stacking a bigger bridge at the end of a smaller bridge.
This is a possible use,
Okay.
right? So ready in for we'll call this 8-bit bridge.
Would it need to change the number of states inside the controller? Would it still be fine to have the same number of states?
Give me 1 second to just draw my diagram.
Okay.
Right? So, kind of the beauty of this, for a module like this,
Yeah.
you would be able to use the exact same controller circuitry.
Uh-huh.
The only difference between these two is the number of wires coming in at this point, the size of these registers, and the number of wires at this point.
Okay.
Which is that's kind of welcome to the beauty of modular design, right? So the manner in which this bridge is receiving data is the same as the manner in which it's outputting data, using a ready signal, right? So it's like a politeness thing. It's like shaking hands, you know?
Yeah.
It's like, I receive data in this manner, I will pass it on in the same manner. That way everybody's happy, right? If a designer is making design decisions based on that type of an interface, not including the ready out signal would be a huge Richard relocation, right? Cool?
Yeah.
Cool.
All right.
All right.
Thank you.
Good. Did we run out of memory?
No, we're good.
We're good? Awesome. Thank you for sticking by a little extra.
No
Sorry,
problem.
Sorry. Oh, I should ask, do you have any questions?
No,
No?
just making sure I got everything.
Cool. Was that helpful, that little extra bit?